Hello everyone, welcome back to the Game Engine Development Workshop series. So last time we started on our Quadtree implementation here. There's still some work to be done on that, and then once we finish that, there's also a significant amount of work that we need to do actually integrating it into our engine. So the first step is just to finish the actual base implementation, then integrate it into our engine, and of course test it to make sure that it was actually worth doing all this work. So I think what I'll do for that is I'll just sort of leave my build and debug mode here, and then we can test it against that like 10,000 whatever hitbox thing that we have now, and just compare performance. And then if we get through all of that, which I'm not sure if we will, then I'll give you sort of an intro into our scripting language, which is what we'll be doing after this. Okay, so when we left off, we had just created this node comparator type here, which is a functor. It simply implements this operator parentheses, like the function call operator. And the reason we did that is down here in our move method here. When we're moving around the tree, our grandparents might change from position to position, and as we leave nodes, those nodes might need to be merged back up into their parents. But the issue was, I talked about it all last video, obviously, but we just needed to make sure that they were being merged in the right order. So we threw this node comparator in there to make sure that the set is sorted in a way such that merging all of them through an in-order traversal of the set, which is a tree, does not cause any issues. So we're done with that. And we are moving on to sort of the next big method of the Quadtree element class here, which is update. So move is responsible for like actually moving it within the tree. So this will be called from our like dynamic class, our dynamic dot update class, or we'll actually define a new method that like will be called before the update class to make sure that the hitbox representing this dynamic is in the correct place in the tree, so it knows where everything is and how to resolve any collisions. So that's the move method, and then the other big method is the update method, and that is responsible for actually detecting collisions, and then somewhat responsible for resolving them. So let's write that. Obviously, our Quadtree element, we do have a virtual function called resolve collision, which is actually what this update method will call, but it still does a significant amount of work in that process. So the first thing we'll check is that we're actually moving, because if we're not moving, then we have no potential to cause a collision, so we can just return. Otherwise, we'll create some places here to store information about any collisions. So I think I'll write it like this first. So we'll have a standard. So the problem we have here is that we can have multiple collisions. And so there are a few ways we could do this. I think I'll just go with the simplest for now. We'll have a vector of collision info objects, which is just a structure we defined as like a child class of this Quadtree element that just stores these three things basically. And this will be called collisions. Now, each Quadtree element can be contained within multiple nodes, and each of those nodes, or all of those nodes, will be in that element's parents list. So we'll go through each parent in our parents, and then we will actually traverse the other elements, or all of the elements contained by that parent. So we'll just start at the front, go all the way through. And this is where we actually need to check if there's a collision happening. So just for convenience, I'll go ahead and sort of extract the actual element from the current element node. And then the first thing is we need to make sure that we're not checking against ourselves, because obviously, if a node contains us, then we will be somewhere in this element node, like linked list. So we need to make sure we're not checking against ourselves. And then the second thing, obviously, is we need to make sure we're actually intersecting. Intersects is also a virtual method that we will have to actually define in a derived class of the element. But for now, just assume that it works. So if we're not checking against ourselves, and we actually intersect with this thing, then we need to actually, we need to create a collision. We need to say, hey, this is a collision, and this thing stores collision info, so we need to give it a time, or I'll just do pushback. Actually, I'm not quite sure what the constructor was. Okay, so we have an element, so the element we're colliding with, and then normal contact and time. So I'll just do this. So the element is going to be cur, then we have normal contact time. Okay, so that's all the loop needs to be, theoretically. Just like that's the bare minimum for actually checking any collisions, is check against every other element in all of your parents. Because remember, that's like the main theory behind this quad tree in the first place, is in order to reduce the number of collision checks that need to happen, you only check against the other objects that are in your immediate area. So that's what we're doing here. Then, once we've determined all the collisions, we need to loop through them again and check that they still exist. So I believe I touched on this in like the theory video, but the reason this is important is it's possible that, I think I'll draw an example here. If we have, let's say we have a wall, and this wall is composed of two different hitboxes, but they're like totally lined up with each other. And we have our player here, and our player is intersecting with both of them. So when it intersects with this one on the right, a new collision info object will be added to our vector. And then also, same thing for this one. So we now have two collision info objects. So we've done this loop, and now we're at this point. So we know what we're colliding with, and now it's time to resolve those collisions. So when it comes time to resolve them, we'll resolve just this one first and then this one second, because that's the order they were added to our vector. It doesn't really matter, though. The point is this, that whichever one is resolved first will push us back out here by reducing our velocity. That's sort of our strategy for preventing collisions. That's what it is, exactly what it is. It's preventing them. It's not fixing them. It's not, oh no, I've moved into this thing, move me back out. It's, I'm going to move into this thing, update the velocity so that I don't move into it. So that'll happen for this one, but then also for this one, regardless of the fact that resolving this first collision also just so happens to have resolved this second one. And the effect will be that the velocity will be reduced more than it needs to be, and you'll get some weird effect. So after we process, like as we loop through our collisions, we need to make sure that each one still actually exists. So we'll just call intersects again with the same, like the same element here. That's why we've stored that. And then just passing in the rest of our like info objects there, contact normal time. And then if we still are intersecting, then we will actually resolve it. Why is that called resolve collisions? That should just be resolve collision. There. Okay. So now back to this. So I mentioned that this is problematic. And the reason for that is that this works just fine to solve this problem that we mentioned here, but what it doesn't solve is a problem that I brought up, I think, last video, at the beginning of last video, which is this effect of if I'm sliding along a surface like this, where there are multiple hitboxes that are like, flush with each other, but they're separate hitboxes, depending on the order that collisions are checked in, which, for any given case, we have to assume is arbitrary. We can't really control that. But based on the order that collisions are checked, they will be resolved like in that same order. And we see that, here we're resolving collisions in some arbitrary order, just going through our map of parents and then pushing them back into a vector and then just going through that vector. So whichever one is added first will be resolved first. And that doesn't really make sense, especially in this case. So just a brief overview of what I've talked about last time. If you're coming at it like this, and this right box resolves it first, you'll be pushed this way, and then this box will resolve it, and you'll be pushed out. And the effect is that as you come here for that frame, you sort of stutter at this corner and you stop, when really the effect should be you just slide along like that. And the solution to this is to make sure that we're resolving collisions in order of proximity. So in this case, that would, obviously be the case. As we're moving here, this, remember that our rays are casted from the center of our player, so in the direction of velocity. So like this ray intersects at this point with this green rectangle, and then that same ray goes on just a little bit and intersects further down the line at this point with this rectangle. And it's clear to see that green comes before blue along the direction of this vector. And it also just so happens that resolving green first, in this case, works out. And I'm not sure. There might be some weird cases where this isn't true, but I am suspicious that this is always true. It's very simple, non-rotating rectangles and all that. So I don't know. I think this is the proper way to do this. Is we just make sure that our collisions are inserted into some type of data set that is, or data structure that is sorted based on the time of collision, so that they're resolved in the correct order. Now, we could do this with, instead of a vector, obviously, because that's not sorted, we could just use like a standard, say, map. Now before, up to this point, we've used unordered map, which is a hash table, which is very fast. Map is similar to standard map, is similar to standard set, which I talked about. Up here is just a tree underneath. It's a red-black tree. So also pretty fast, but importantly, sorted. An unordered map, obviously it's in the name, not sorted, but a map. It's a tree, and so it is sorted. And the thing we need to sort on, very simply, is time. Whatever value we get back from checking a collision is, remember that's going to be some value between 0 and 1 for like the velocity vector of that frame. So say, this was a bit confusing, but say my whole velocity vector, like really my player wants to end up here. And so this green point and this blue point will be values between 0 right there and 1 right there. And so we just need to make sure that green gets pushed further left in the tree than the blue one does. And map will handle that automatically for us, just because of what it is. If we map floats, floats are the keys, so maps are sorted by their keys. Float being the time, and then the element mapped to that float just being our collision info. So we could do this, and then obviously we'd have to change this just a bit with collisions dot in place time, and then that. So and that probably won't work, actually. We might need to set that explicitly. Yeah, so in this case, like there is a bit of redundancy because we're storing time twice, but whatever. Just it needs to happen. But there's an even further problem here, which is that maps, just by definition, map a key to a single value. And what that means in this case, and why that's a problem, is that if we somehow have two time values that just happen to be the same, then one will get added, and then another one will come along with the same value, and that'll get added too. But because it already exists, whatever collision info structure is in the map already will just get overwritten. And so our loop here will think that there's only one collision, when really there are two. They just happen to have the same time value. And this sounds like very far-fetched and like not at all plausible, but it's actually very common scenario. There is a very common scenario that exploits this and causes a pretty serious bug. And this was very difficult to debug. But I'm glad I figured it out, and it was sort of satisfying to figure it out. So let's take this case. You know, extremely common, obviously, in a world made up entirely of non-rotating rectangles. My player's in a corner. So say my player is like perfectly, like pixel perfectly in this corner already. They're like the same amount. They're like perfectly lined up on both of these axes. So this right side of this one, I'll color these again just to make it clear. So the right side of the green one and the bottom side of the blue one. And in this case, they're moving this way. Actually, I'm going to take care to draw this line especially accurate. They're moving like that. Now, what do we notice here about the time, the point along this vector at which it collides with the green box and the blue box? Well, the green one is right here. It's on the corner. And so is the blue one. They are exactly the same time. And so in that case, say we check the green one first arbitrarily. So our map will now contain, you know, a collision info struct about this object. But then we check our blue one later on, and this one gets overwritten by this one. And the effect that that'll have is our player will just slide right through the green box, just like that. And once you're inside a box, remember, our system doesn't have any way to resolve existing collisions. It is a collision prevention algorithm. That's just how it works. And so once you're inside this box, even a little bit, that's it. You're inside. Like there's no fixing that. And so you'll just keep sliding right on through and just pass right through the corner. Now, I messed around with doing this, like fixing this problem a similar way to how I fixed this one up here, where I defined like a custom comparator just for this map for collision infos that would like, it would like, because the issue here is that we can have keys that are the same. And so I tried messing around with coming up with like a custom key type that stored not only the time, but some other stuff as well that would be unique to each collision. But it was kind of weird. I couldn't really like get it to work. And eventually I discovered that there's actually another standard container that is built, like it solves this problem just inherently. And that's called a multi-map, which is exactly like a map, a tree, you know, underlying structure. It's sorted, maps keys to values, but each value can have, or sorry, each key can map to multiple values. And I think that's all we need to change, actually. It's just the type of that one variable. And that's it. So, oh, not map, multi-map. So at this point, in our example here, when I guess blue gets resolved first, and then later on green is checked, green will also be added. Purple here just representing that our loop there knows that this is a collision. So blue will not be overwritten, but green will also be added. And of course, then the result is that we can't pass through either of these boxes, and we correctly stay in the corner. Okay. So hopefully that was interesting. That was a neat sort of problem that came up, but also one that was very frustrating and sort of scary to deal with because, you know, like sort of put yourself in my shoes where I'm writing this thing. I have no idea what's going on. So is it something wrong with like the way I'm resolving collisions? Is it something wrong? Like, have I totally just miscalculated this whole structure and it's like not going to work at all? No, thankfully, it turns out it was just, I was doing something dumb here and skipped over the obvious case of being in a corner, obvious and common. But yeah, that's our update function. So that's why I said this one does quite a bit of heavy lifting. It does have to do some logic and just sort of understand the rules of our world and know that collisions can exist at the same time. But ultimately, there is also a lot of the work passed off to these intersect and resolve collisions methods, which we will also write today. So that's actually, I think, most of the big functionality in our Quadtree element. There are quite a few methods left to write. If we go up here, we can see there are quite a few. They're mostly just helper methods, and then at the end, once we've done those, we'll sort of wrap everything up by just tying up some loose ends here, making this a bit more efficient. In particular, this update function actually. We'll look at how we can make this loop more efficient. But for now, let's just move on to the next one, which is add to. So this method will be called when adding an element into our tree. And the reason we have a separate method for it instead of just like doing it in the node class itself is because our Quadtree element is going to maintain some like additional state about its parents and such. So it's nicer to keep it in a method here. But first thing to do obviously is just make sure we have a parent. So it'll probably help if I show you where this is actually being called from. So this is in the, I think the first method we wrote, which is Quadtree node add. So right here, when we get to the actual point where we have a non-divided node, so we're actually storing this element, we create an element node for it. An element node is just a linked list node that stores Quadtree elements. And then we call this e.add2. So the node parameter is going to be this, which is this Quadtree node, and then the container parameter is going to be this element node. So that's what these two are, node and container. And our map stores a pointer to the Quadtree node that contains it, as well as its place within that Quadtree node, just so it knows exactly where it is and it doesn't have to do any searching or anything when it needs to update. Now, we also have to account for the parent of this parent node, or this Quadtree element's grandparent. So if it exists, which basically just means we're not being added to the right into the root node, then we'll just add it to our grandparents list. Because we don't want to insert null pointer here because there's no reason to. So we'll just check that it exists. Okay, now we have sort of the inverse method of this, which is remove from. Sure, you can imagine what that does. So the first thing we'll do is erase that node as our parent. And then we have to do a little bit of extra work here. And this is another thing we'll come back and sort of tidy up to make sure that we can remove this parent node's parent. So we can remove a grandparent here. Because what can often happen is a Quadtree element is added to multiple nodes, but those nodes share a parent. So let's say I have this, where this is my root, and I have some Quadtree element A that's added to this node and this node. Well, both of those have the root as their parent, so this Quadtree element A has root as its grandparent. And now let's say, so this, I guess I could draw this. What this sort of represents is like being in both of the right-hand quadrants. So let's say this is my element A, and it's in the top right and the bottom right nodes. And now if I move down here, obviously I'm not in the top right anymore, so I need to get rid of that. So that's when remove from would be called. Now at this point, I don't want to just blindly erase the root as my parent because that's not fair. I'm still contained, A is still within this other node that shares the node we are being removed from's parent. And so we need to make sure when we're removing that this parent, that this node is the last node whose parent is a parent in our grandparents list. I'll just write it. It's hard to say. So if the parent exists, again, we will just go through all the rest of our parents and check that their parents aren't the same as this one's parent. And that cannot be called parent, actually. I'll just call it P. So P here is going to be a Quadtree node, and each Quadtree node stores a pointer to another Quadtree node, which is its parent. So we just compare the parent of each of our other parents to this parent's parent. And if we find it, then that means that we can't remove this object from our grandparents list, because some other one of our parents has this parent, and so we can't remove it yet. But otherwise, so if not found, if found is still false, then we'll just go ahead and erase that. And obviously this is kind of bad because we're looping, but again, we'll come back to that later. Okay, now we have a whole bunch of super simple methods. One is delete, which just takes this Quadtree element and removes it from the tree entirely. So we'll remove from all of our parents, merge our grandparents, and then get rid of those. But so that takes it completely out of the tree. And then let's actually write this remove from parents method here. So this isn't just going to like clear this element's set of parents or map of parents. It's actually going to go to each of those parents and remove this element from their list of contained elements. So again, it's like actually taking it all the way out of the tree. And this is where storing this value in our parents list, this element node, the element node at which this element is located in that node, that's where this comes into play. So parent.first will be the actual Quadtree node, and then we'll call delete element on that Quadtree node. And delete element takes, it needs to know which element to delete, but we're storing that, so we can just pass it. First is the Quadtree node, and second is the element node. And then we can clear the parents list as well. Okay, so let's look at some small optimizations we can make here. So I have one last slide here. So let's say we have a tree like this. So I've only shown 2 rectangles here, obviously, but just assume that this like is divided like this. So we can see that these are a part of many quadrants, and that some of those quadrants they share exactly 6, marked in green there. And clearly, there's no need to check that these 2 objects collide 6 times, because it's always going to give the same result. Because it's just checking the same 2 elements over and over again. So in our update method, what we'll do is we'll just keep like a list of all the objects that we've already checked against for that frame, and then that means that on later loops, as our loop keeps going, we won't check against objects that we've already checked against. Because right now, the only condition we have is that we're not checking against ourselves. But now we can also check that if we've already marked this as a collision, we don't need to mark it again. That doesn't make any sense. And the best structure here that we can use is just a set, because we don't want any duplicates. Not that we would have any, I guess, but we don't want to like resolve this and then, I don't know, you'll see. So we'll just use a set. And also we don't care about order, so we'll just use an unordered set, which has this nice benefit of just order 1 everything, theoretically. Now, this comes back, this is like something I mentioned in the last episode, is that I have some things in this file in particular that I have done, like I haven't actually tested that they are faster, and it might be difficult to test that, but theoretically they are faster. And one of those things is allocating, just making sure we allocate on the heap as little as possible. So I mentioned this last time specifically with regards to the set class, which I said is something that it essentially has to be allocated newly every time you use it, because each it's a tree underneath, and so each node in that tree, when you remove that node, like its memory is deleted. It's not something that can like stay reserved necessarily, or it's not something that is. But for unordered sets, those are just arrays. They're just hash tables, and so those we can absolutely allocate once and then just like clear them every frame, but maintain that memory, so we don't have to allocate a bunch of memory every frame. So that's what we're going to be doing. We'll add another field to our Quadtree element, which is, I have chosen to mark it mutable. Not that it actually like matters in this case, because it's not like a way to get around the const rules. I just think that this is a good bit of documentation, essentially saying like, hey, this is just for convenience. It doesn't actually affect the inner workings of this. It's not like something that you have to worry about. So I've just marked it as mutable. Now another thing we'll go ahead and do is define our move constructor, because we'll need to do this eventually. So just might as well get it over with. Just copy those vectors there. And then we have three other things. We have parents, grandparents, and checked. And these we could do like this. We have, just like call the constructor with the other element's object, but that calls the copy constructor. And theoretically, again, this can be made more efficient by instead calling the move constructor, which essentially just juggles the pointers around in memory and makes sure that nothing is actually reallocated, nothing is copied. So just save a bit on time there. So we'll just move all these other ones into here, and this should probably be no except as well, for whatever reason. Okay. Now in our Quadtree element constructor, this is where we will actually be doing the allocation of this object. Again, we want to allocate once, just when we create it, and then never have to again, basically. And for this, I have chosen the arbitrary constant size of sMapReserveSize, which if we go to that, is just threshold cubed. And this, again, is arbitrary. I think it probably should be some multiple of threshold, just because, remember, threshold is like the maximum number of objects that a node can contain. And so it should somehow be related to that in some proportional way. But this really doesn't matter. The main point of this is that we are storing this as part of the object rather than reallocating it every time the update method is called. The initial reserve size might be too big, in which case, great, we have more memory than we need, so we're not going to have to resize. It might be too small, in which case, oh well, we'll have to resize a few times. But at that point, like, it's not going to downsize automatically. So yeah, the main point is just that we are storing this as part of the object. And then in our update method here, we'll call mchecked.clear, which does not release any of the memory. It just gets rid of the objects that are, like, it sort of clears the array by just setting all the elements to null pointer. But it still has that memory. And then we can do an additional check here. I'll actually split this off into two separate if statements. So if we're not checking against ourselves and we haven't checked whatever object we are on, this frame, and I probably can't do that. I might have to do it with iterators. I think the contains method is a C++20 method. So if we're not checking against ourselves and we have not checked against this object, this frame, then we will actually check for intersection. And once we're inside of here, this means that we are checking some element for the first time. And so we need to mark it as checked, regardless of whether or not we collide with it. We'll just do mcheck.insert cur. Okay. Now our remove references to method, or remove from, just removing like all references to this node here, this is a loop, and that's bad because that scales linearly with the number of parents we're in, which depending on the distribution of stuff in your world can get very, very high, very, very large. If you have a lot of small things moving around and your tree has to subdivide a bunch to account for them, then bigger objects will be contained by a whole bunch of parent nodes, and so we'll be looping through a whole bunch of parent nodes here, which is not good. Even though that's sort of an edge case, it's very simple to sort of remove this loop here, so there's just really no reason not to. So we'll have another mutable thing here, again, really only for the purpose of just marking this as non-essential, basically. The same thing we do here. And all this is going to do is for each grandparent that we have, it'll keep a count of how many of our parents share that grandparent. So the first time we add a node and it has a unique grandparent, this count will be set to 1. And then if we add another node that has that same parent, then we will increment this to 2. Then if we remove one of those, we will decrement this to 1. And because it's still 1 and not 0, we won't remove that grandparent. And obviously this is all a map, so it's very fast. And it just removes that loop, more importantly. So we need to modify our add2 method here to account for this. So if we have a parent, I guess I shouldn't have deleted that. We have a parent, we'll add it to our list. And then we'll see if we already have that grandparent. Because this will take care of just making sure there are no duplicates, but I'm not sure if it might have some return value. I think it returns an iterator. I'm not sure. It might have some return value that like marks whether or not this was actually inserted. I don't know how it works, but we'll just check our grandparent count to see if we already have this grandparent. If we do, then we will just increment that count, the one that already exists. If we don't, so this is a new grandparent, then we need to add it. So mGrandparent count at parent equals 1. So that'll take care of the add logic. Now we just have to update this remove logic. And this actually now becomes super simple because we will write another helper method. So just if the current node we're removing from has a parent at all, then we will try remove grandparent on that. And all this is going to do is check if the count is 0. If it is, it'll actually remove. Otherwise, it'll just do nothing. And that takes in a... Okay. So we'll get this grandparent. We'll subtract 1 from its count because it's now been 1 fewer node references that. 1 fewer node has this node as its parent. And once we've decremented that, if the count is now 0, then we'll remove it from our count list. And remove it from our grandparents list. Okay. So now that we have this, like this is our Quadtree. It's done. This is all the code we'll be writing in this file. Before I move on, actually, I should just test that it compiles, so I don't have to come back and fix a bunch of errors. Wow, seems to be good. Okay. So at this point, we need to actually like take all of this logic that is currently just sitting in our main function, like this ugly static thing and this rect class just for testing. We need to actually properly do all of that and make use of our Quadtree. So the first thing I'll do is create a new method in the math class. Oh, that's probably why it's all compiling, because it's not even being included. I knew that was suspicious. Now let's try. Yeah, there it is. Try again. All right. Okay, so I'll just write a method to check whether or not two rectangles intersect. And this is going to be using that axis align bounding boxes thing I mentioned way back at the start. And this will be used, as we'll see, to actually check whether or not a given Quadtree element is contained within a given Quadtree node. Because that sort of thing doesn't care about velocity. It just looks at current position, and so we don't need to do any sort of raycasting or anything. We just need to check if the two static, essentially static rectangles intersect, one being the area that the node controls, like that region, that quadrant of space, and the other being the entire area that the hitbox takes up. So we'll take in the A's position, A's dimensions, and then do the same for B. So two rectangles, A and B. Then we can use our range class to define a range for each of these ranges. So one for like the range in the x-axis that A spans, and then we'll do the same for Y, and then the same for B. Okay. And all we have to do here is check if there's overlap between both of these ranges. So if AX and BX overlap, meaning that there's overlap on the x-axis and there's overlap on the y-axis, then our rectangles are intersecting. And for the sake of completeness, we can just go ahead and throw on a range overlaps. Structure here, and just pass that to Is this yelling at me? Not sure. Seems to know what a range is. I don't know. We'll come back to that. Not important. So this will be used when actually inserting elements into nodes. But that's obviously the easy part. The harder part is the raycasting stuff. So for that, we'll define a new class here, ray.h. So we'll have two vec2s, direction and origin. Then we just need a method that's basically going to be the one here, this ray rect method here. So I'll actually probably just copy that, take that, stick it in there. It's not going to be static. You can give it a proper name now. Intersects rect. So don't need origin and direction. We have those. But we don't have a rect type, so we need, I guess, a vec2 of position and dimensions. Okay. Looks good to me. Let's include this. It really does not like this, huh? Not sure why. Did I just spell it wrong or something? Oh, it's called range overlap params. Huh. That's annoying. Hopefully that's not all over the code. Okay. Looks good. So now, at this point, we have all the tools we need in our math library. We have our Quadtree to actually handle all of this, like managing where everything is and knowing which collisions to resolve, so on. And then we have this additional method just for helping out with the Quadtree, and then we have the ray for actually testing intersections. And so at this point, we need to come back here for a little bit. Well, not really, but come back and look at what we still have left to do. So the Quadtree element, we need to write implementations for resolve collision, as well as is contained by and intersects. Now, the reason I've done this is because there's not really a reason to make it so that this Quadtree can only handle non-rotating rectangles, because it doesn't really care. It shouldn't care, at least. A Quadtree is just sort of, it's like an abstract representation of any 2D space. It doesn't matter what's in that space. And so this sort of design choice here has made it so that you could take this, and depending on how you override resolve collisions as contained by an intersects, you could make it apply to any 2D geometry that you want. And the Quadtree doesn't care at all. It'll handle everything correctly by calling these methods that you have implemented. Of course, in our case, we are just doing the simple case, but still, it's nice to. I think it's nice to have that level of extendability. Okay, so I'll go ahead and define a constant here, Quadtree threshold. I'll set it to 4. I would say it's very likely that if you were to do benchmarking on this, with some specific distribution of rigid objects within your world, and do the same thing every time, then you would likely find that some value higher than 4 would be good, because 4 is not very many. That means there will be quite a few subdivisions if you have a lot of objects. Again, depending on the distribution, but if you keep all of that the same, then I think you'll find that something, maybe just double that, 8 or even 16, would be fine. But for us, I'll just do 4 because, like in all the examples I've shown, it's been like 3 or 4, and it's just somewhat easier to think about if it's low. but I've defined it here just once so that we can, tweak that as you need, and it'll just be the one line. Okay, so now we will actually, in our world class, we will create a Quadtree element implementation. I'll call it Hitbox. So it will extend from, no, not Qt node, from Quadtree element. And all we have to do is give it some constructors, some basic constructors. This is just going to pass down all the values. So position, dimension, velocity, and then the root node. So the root node doesn't actually get passed down because in our, in our element constructor, we don't add it to anything. We just sort of initialize it with the given values. And this can't, like, it would be nice, and it would make the most sense to, whenever you create an element, automatically add it into the tree. Because if you're creating an element, it should be in the tree. You're going to add it to the tree no matter what, so why not do it automatically? But the reason is that adding to a node, the node.add method is contained by, which is pure virtual. So we can't call this from within the Quadtree element because Quadtree element class doesn't have an implementation for that method. So instead, we sort of have to push it off to any child classes, and those can call it, because Hitbox, this is where we're actually going to implement is contained by, and the other ones. So here, we'll just check if fruit exists, and then add ourselves to it. I'll delete that. We do actually need this. And we can just invoke the elements move constructor by doing standard move on that. And this we might be able to see here what the compiler can catch. Ah, that's very nice. Yeah, so it says Quadtree element, blah, 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 const element single ampersand. So what's that? L value is deleted. So the copy constructor is deleted, which is perfect because we don't want to do any copying. So we will instead explicitly call move and invoke the move constructor. Okay. So now we have resolve collision, which just takes in a collision info. And all we're going to do here is what we are doing in here. This line, we're just going to change our velocity to make sure that whatever collision is going to occur doesn't occur. So the info structure stores our normal vector. Please feel free to actually do this correctly with the dot product if you are smarter than me, but I haven't put any more time into figuring that out. Here I'll just define a static overlaps params to, because this is going to be used to check if this hitbox is in some node. And I think I can explain a little bit about why I've chosen this, but let's just write it first. So we have is contained by, which just takes a node. And we'll use our new rect intersect method. with the two rectangles. I'll just say the node is rectangle A, so we need node dot get position, node dot get dimension, and then we'll just pass ourselves impos and imdim and our overlaps params. Next we have bool intersects. Which takes Quadtree element and then all the stuff that's in a collision info. I'm not sure why I'm not passing a collision info here. I probably should be. That would just be cleaner. But there might be some reason. Okay, and here's where we're going to do the actual raycasting. There's not really a good way to show this because I already deleted that original ray rect method we had that was doing that, but it wouldn't have worked anyways to just copy it. Sort of have to reformulate how we're thinking about this. So we need to create a ray from ourselves, from this hitbox, and check it against this other hitbox. So the ray is going to start at the midpoint of this hitbox, and position and dimension are different than how our dynamics handle them. Or dynamics, if you remember, position is the center point of it, but for these, position is the bottom left corner. So in order to cast from our center, we'll have to give it our position plus half our dimension. And then the direction of that is going to be the velocity, our current velocity, times the frame delta. So how much we will actually be moving this frame. And then we can call intersects rect, and of course the rect that we're intersecting with is sort of artificially inflated because we're doing all this raycasting on the midpoint, but we need to make sure that the actual rectangle itself is not intersecting, not just the midpoint. So we'll take the position of our other object, subtract half of our dimension, and then for the dimensions of that other object, we'll take the original and then add our dimensions. And this will just ensure, this I showed maybe last time or the time before, just make sure that it's not the midpoint that's not colliding, it's the whole rectangle itself that's not colliding. So this is yelling at me, it probably doesn't match. I'm not sure why that doesn't match. This one certainly doesn't match. Let's see what that's about. Is contained by, it's const. Why does that not work? So we have 4 vectors and then range overlaps params. Of course. Node dot get dimension is just a uint because our nodes are always square. So we need to explicitly create a vector here. With that, oh, we don't have the constructor yet. That just takes one. What else is wrong? That should work. Okay, so anyways, this the reason I have these overlaps params, what this says, like thinking about the effect this actually has, is these specify whether or not the range checks should be inclusive, and saying true means they should be. So in this case, it's on both ends. We want greater than or equal to and less than or equal to in all of our calculations. And the effect this has, remember this is going to be called from our from node, when node is trying to add some element. The effect this has is very important and actually necessary for proper operation. So if we have, I keep doing that. We have like some red object here, and some blue object here that's moving, say they're like this, where they are perfectly touching. Now we have this conundrum, which is, let's try and draw the tree here, the underlying tree. So here, obviously, we have, I'll call them A and B. So B is in the bottom right, A is in the top right, but B is also on the border of the top right. So should it be in the top right or should it not be? And the answer is yes, absolutely, it needs to be. And the reason for that is if it is moving on this frame. So at the start of this frame, it is perfectly lined up here. It's like exactly on the border of this top right. And if it's moving in such a way that it will intersect with A on this frame, and it's only contained by the bottom right node here, it's not going to get checked against A. And this could not be a problem. It could be fine, because in this case, if the velocity ends up here, then next frame it'll get pushed back out. That might give you a bit of visual jitter. It probably would, in fact, based on your frame rate. Just because for one frame it will actually like move inside. Oh, actually no, there wouldn't be any visual jitter. It would just pass right through it. Exactly. So yeah, this is always a problem because again, this is collision prevention. It is not collision resolution. And so like once B is even a little bit inside of A, it's stuck there. So on this first frame, if it moves even just this much inside, and even though now in this case it would be in the same node as A, and so it would be checked against it, it's already inside it. And so our algorithm will say, okay, that's not an intersection. I'll just keep passing right on through. And so that's why we have that sort of double inclusive range check on both sides. Let me see if I can compile this. I'm not sure what this is, just some dumb error it's giving me. Rect intersect identifier not found. Oh no. Oh. That was it? Probably not. Oh, I guess. Huh. I'm not sure. Okay, so that's our hitbox. I guess I'll just go ahead and fix this. This is annoying me. We can get rid of all this junk from in our main file now. Ooh. Actually, no, I don't want to. I'm gonna leave all this because we can do some benchmarking here. We want to compare the performance of this, which even though it's messy, is like exactly the same functionality we would have anyways. So we want to compare this old like clunky method of just in squared essentially. In this case, it's just in because we only have one thing moving. But even then, we'll see massive gains. So we'll compare this to our new system. But in order to do that, we actually have to get all of this integrated. So we've taken the first step here, which is creating a hitbox class that actually like defines all of these. So our Quadtree elements are well defined here. They know how to interact with the world, with other Quadtree elements. Now we just have to attach them to things. So there are two things that need hitboxes. First is dynamics, and second is just stuff in our world that is rigid. Because if we look at our tile class, we have this like Boolean rigid that we have implemented, like it exists and our map file reads it in, but it doesn't do anything yet. And so we need to make that do something. And for that to happen, we need to add like some knowledge. We need to make Quadtrees part of our map pipeline, because that's really what they are. Like they are separate, and that they're a separate class, obviously, and they're pretty heavily generalized. But in this case, every map needs to have a Quadtree because every map might have things that need to collide within it. And so the way we'll end up doing this actually is giving each chunk its own Quadtree. Because in the sort of weird, like messy general case map architecture we have, each chunk is theoretically independent of all other chunks. Like there's no intersection between them spatially, and so they should all have a separate quad tree. They don't have to. That's not a requirement, but it is an efficiency thing. Because say I have some chunk here, and then some chunk up here. I absolutely could do this and say, okay, they all share this one quad tree, but it would be a lot more efficient if each one just gets its own small quad tree. If each chunk gets its own small quad tree. Because then fewer divisions have to happen, there are fewer elements contained in it overall, so it'll just be faster. So we will give each chunk its own tree. So let's start in here in our chunk class. We'll add a few things. We have position. Now we also, so as part of this, we will actually like implement the functionality to make sure that only one chunk is rendered and processed on any given frame, because that's sort of the whole idea behind it anyways. But right now we're just drawing all of them. But at this point we have like enough groundwork set that, you know, we have a player who's moving around and we can check whether or not it's in a given chunk. So in order to do that though, we will need a position for each chunk as well as its dimensions. So sort of like same as its quad tree, like the minimum and maximum point of stuff within it. So the area that it spans. We will need a Quadtree node, as well as a vector of hitboxes. And I'll explain why that's necessary. I should include hitbox. Okay. And now we have, well, yeah, we need to actually update this, importantly. And that, but the important thing here is that we delete, well, not delete, we remove the original chunk's reference to this quad tree. Otherwise it'll get deleted and then we'll have an issue. Okay, and I'll just add a couple of getters and setters. Or, well, not setters, just getters. Okay, and then in our chunk constructor here, we need to initialize all of this. We should set Quadtree to null pointer. And at the very bottom, well, not there yet actually. Very top. So we need to, as we're looping through our vector of tiles and adding them all, we need to keep track of the minimum and maximum points that any tile touches. And that way we can calculate our dimension. So in order to do that, this is not like super important, but it's just something like weird that you may not have seen if you've never done I don't know, game stuff before. I've found that this type of thing comes up quite often in game programming, but I guess you would also see it in like sorting algorithms maybe. But we need to give some initial values to our minimum and maximum points. And we can't just give them anything. Like we can't give 0, 0 for both, because everything in our world might have negative coordinates, and in that case we would say our minimum is 0, which is not. So we'll sort of like set them initially to the opposite of what they are. So minimum being the maximum float value, and maximum being the minimum float value, means that for any for any object with any coordinates, they will, like, the first tile will always overwrite both of these, because any coordinate is less than fmax, so min will be set, and any coordinate is greater than fmin, so max will be set as well. And just real quick for peace of mind, I'm not sure if numeric limits, I'm thinking that min might return something very close to 0. I highly doubt that, but just to check. Float float min. Where'd it go? It's not here. Minimum normalized positive value. That, I'm not sure. That might that might be very close to 0. Well, I saw there was another in here. Lowest, which is negative float max. Okay, yeah. So wow, I'm impressed that I caught that. That should actually be negative f max, I think. Or why don't we go ahead and just use lowest? Okay, so that was some value like extremely close to 0, when what we wanted is some value extremely close to infinity, some really large negative value. So that'll fix that. That was an annoying bug. Okay, so now when we actually go through our tiles, we need to update these values accordingly. So min.x will be the minimum of the current value and the current tiles value. Same for y there. Then maximum will be that. Remembering that a tile's position vector is its bottom left coordinate. So we need to make sure that the top right coordinate is what is checked against as like being in bounds, not the bottom left. And then if the current tile is marked as rigid, we will add it. We'll create a hitbox for it with its position, its dimensions, velocity, which will just be 0, and the current node will be null pointer because we're not going to add it yet. We will add it at the very end here. We'll actually create our quad tree, because this constructor takes the minimum and maximum points, and now that we've looped through all of our tiles, we actually know those. So we can do that. And then we need to go through all of our hitboxes and add them to the tree. Now, why do we need to store these hitboxes? Well, the reason lies in that little red squiggle it's giving me there. I'll just go ahead and set these though. The dimension is max minus min, and the position is min. So position bottom left, same as everything else. So this is not going to work because add takes a Quadtree element pointer. And so we can't just give it a Quadtree element. And the point there is that nodes don't store their own data. They don't own the things they contain. They only have, well, that's not entirely true. But the things they contain must exist elsewhere. And if this hitboxes vector was, local to this constructor, like we weren't actually storing it as part of the chunk, then this would be a stale pointer after this constructor ends, because once you reach this brace, all the local variables here get popped off the stack. So this pointer points to some place on the stack that is now either not in use or something completely different. And so we need to make sure that it remains valid for the lifetime of our program. So we do actually have to store the hitboxes on the chunk itself. Okay. Now we can go up one level to our map. I'll just add, well, first of all, we're going to change our draw method here. We still need a render, but we'll also type in a dynamic that we'll call our player. And this is what will be used to calculate like the current chunk. We'll have a method to get the quadtree of the current chunk. And then, of course, we need to store the index of the current chunk. Okay, now we need to implement this method in our map. So this is pretty simple, but we are going to do like a bit of an additional enforcement. Because our rule is that we want only one chunk to have to be drawn and processed at a time, which by necessity, that also means that no chunks can overlap. Because if there were chunks overlapping, then the player would have the potential to be in multiple chunks at the same time. And so it would be definitely best to actually check that there are no overlapping chunks as you create your map, which you could very, very easily do, like in your constructor here. But that would just be totally boring. It would just be a complete retreading of like all the rectangle checks we've already done today. So I just left that out. So instead, what we'll do is like just so that we do actually have like some system that works instead of just leaving it completely for you to implement, is we'll just print out an error. Like we won't tell the user like at creation time, like, hey, you have overlapping chunks here, here, and here. Just if our player moves into a space that there are overlapping chunks, we'll just yell at them. So we'll go through each of our chunks. Like that. And we'll use the same intersect method on the chunks rectangle and our player's rectangle. And if we've already found one, so if we've already found a chunk that the player is contained within, then we yell. But again, we can't actually do anything. Otherwise, we will set I as the current chunk and set found to true. Oh, that can't be const. Why is that const? Suppose you could mark current chunk as mutable if you wanted. I'm not sure. I haven't thought about that. And same way as this, if we're in multiple chunks, then we yell. But also, if we're not in any chunks, then we should yell as well, because that means there's like some hole in your world. Basically, the player can just walk out into the void towards infinity, which is not desirable. And then finally, we will take our current chunk and draw only that one. Now this loop as well also is sort of bad. Again, this is like a dumb general purpose map system, but depending on your actual use case, like these chunks should probably be sorted and stored in memory, partitioned in some way based on their space. Because if you have a lot of chunks, you don't want to have to loop through all of them every frame. You want to be able to quickly figure out which chunk your player is in, and that means different things depending on the type of game. So we'll just leave it at that. But that is probably would be an area, a big area for speed up. Again, depending on your use. Okay, so that's all we need in our like static pipeline here. Now we actually need to. Oh no, it's not. Not quite. Oh no, it is. Never mind. Yeah, it is. I was thinking that we would need to add something to the another vector to the chunk constructor to store hitboxes, but I remembered we're just checking the rigid property of tiles, so we're all good there. We just need to add it to our dynamic side now. So each dynamic will have its own hitbox, and we'll change the constructor here a bit as well, because it now needs to contain. Well, it now needs to take in some node that it should be added to. So we'll add that to our list of constructor parameters, and then we'll have some additional methods here. One is move hitbox. Second is resolve collisions. And then, of course, actually store a hitbox. Okay. So now, oh, that's. Where did I put it? World? Ah, there it is. Okay. So taking in that, initially we'll just set our hitbox to null pointer. Then we will set our state, so make sure that the given state is valid. Update vertices for the first time, actually generate the vertex data. And get our dimensions. And then finally, create our hitbox. Object is not allowed. Intersects. Huh, did I not override something? Oh, I didn't mark this as override. Obviously important. Of course, that doesn't match as well. Oh gosh. I'll just copy all that. I think I just typed something wrong in there. I'm not sure. I don't know why that's yelling at me, but I don't care. Okay, so we'll just ignore that for now. But the important part here is that we do actually specify root, because you want to make sure that your hitbox is added to the tree, like when the dynamic is created. And the reason for this, obviously now it's like hard to miss because of the way we wrote this constructor, which is you need to pass in some value there. But when I was developing this, I had this as as a default value, which was very annoying. A default value should be used extremely sparingly because they can produce very difficult to track down bugs. Because what was happening is I wasn't passing that in, and it wasn't yelling at me because it said, "Oh, okay, I'll just use null pointer," and then it doesn't get added. And it worked fine for the most part, but the first frame you could clip through stuff because the first frame, your hitbox hadn't actually been added to the tree yet. And so it was just really weird. And then again, super hard to track down. So just a word of caution there. Okay, now we have these new two methods, which I'll just move up here close to update because they're related. Move and resolve collisions. So move hitbox is it needs to be called every frame because it's going to recalculate all of the stuff that our hitbox contains. Because remember, our dynamics, like the values in our dynamic and the values in our hitbox, aren't actually linked. They're copies of each other. And so every time our dynamic changes, our hitbox needs to change as well. And specifically, this needs to happen every frame. Because our dynamic is moving, maybe moving, so its position is changing, but also its dimensions could be changing because dynamics have multiple sprite states, multiple different sprites, and they can have different dimensions, and so that needs to be properly accounted for. So we'll just do sort of the same thing here. Except instead of creating a new one, we'll just call move. Okay. Now, resolve collisions, we'll just call update on our hitbox, which will go through all the things that it's next to in the tree and resolve any collisions and update the velocity. And then once that's done, our hitbox will contain the proper values for velocity, but our dynamic will not. And so we need to update that. And I'll do position as well, even though our implementation doesn't do anything with position. Some might. It wouldn't be too uncommon to resolve, actually resolve collisions rather than just prevent them. And again, this will be the bottom left, so we have to add that to make it center, make the position the center of our dynamic, because otherwise it'll just drift infinitely far away. As this value, which is the bottom left, gets set as the center, and then you can see it'll just continue like that. Okay, so we have a good amount left. I think I'll leave it there because I can feel myself starting to rush, and these last bits are just as important as the rest of it, actually finalizing, integrating it all. So I don't want to rush through that, and I also don't want to give you a super long video. I mean, already an hour and a half, but I sort of want to keep it close to that. So I think I'll just leave the remaining bit for next time. It'll probably take 20-30 minutes. And then we will actually get started on our scripting language. But first I want to figure this out because this is annoying me. Oh, is that also not marked as const? Oh my god. Okay. Just one final check to make sure everything's good. Probably not. Oh, it's clearly not. Wow. Ooh, that's interesting. I like that. Okay, so now that our Quadtree, there are quite a few issues. Okay, so these, I won't fix, this is just saying, the dynamic constructor is broken, because it is, because we added a new thing. But there are also some issues in our Quadtree. So one is expression did not evaluate to a constant. Well, I don't know what that means, but maybe I'll just change that to const, and that'll probably fix that. And then add to does not take one argument. Takes the node and the container. Oh, yeah, that shouldn't be add to. add2 is called by node.add, so this should be child add cur data, like that. Some other stuff here. Oh, it looks like I didn't update the merge node comparator. And that looks like it. Yeah, okay, but a whole bunch of warnings here still. I wonder what that's about. Oh. Yeah, get dim as a UN. That's annoying, but whatever. Just make the compiler happy. Okay, that looks good. We now have this other one. Function takes, like, I don't know, whatever that is, of the stack. We'd probably had that before, actually. It just everything was compiling, so it wasn't showing that error, that warning. But this is just, I think, because we have like 10,000 of these rectangles just stored on the stack, which is fine, whatever. Like, I don't know. But yeah, so I'll leave it there. This stuff is broken. That's fine. Don't worry about it. But everything else should compile, and our Quadtree should actually be finalized now that we fixed all those remaining errors. So next time we will finish integrating this into our engine and then do that benchmarking, as I said, to see that all of this was worth it, and then get into our scripting language. So I hope you're excited for that, because I certainly am, and I'll see you next time.